Welcome to next lecture. In the previous lecture, we just started single phase half wave phase control rectifier by using SCR as a main device, and we discussed resistive load, inductive load and pure inductive load. Now let us take few more conditions in the load side. Here I just drawn the circuit with a RE load, okay, for readily reference. Now, just like earlier, source voltage Vs is equal to Vm sin omega t. As per our notation, we are representing source terminals with A and B. Output side, the load terminals are representing with X and Y, and load voltage is V0. And output current is denoted with the symbol I0. Voltage across SCR is represented with the symbol Vt. Now, when the load has EMF term, one of the important parameter, that is theta. What is theta definition? Sin inverse E by Vm, just like in the previous diode circuit. So, one of the important condition for SCR to start conduction. Suppose if this EMF is not there, there is no condition. Anywhere from 0 to pi, we can supply firing angle. But as this load has EMF term, now just look into this voltage waveform here. This is a theta, and this instant is pi minus theta, this instant is pi, isn't it? Next cycle, this angle is 2 pi, and here this is a 2 pi plus theta, and this is 3 pi minus theta, and here it is a 3 pi, right? So, for SCR to start conduction, what is the basic requirement? Firing angle should be supplied after theta. Okay, firing angle should be supplied after theta, right? Otherwise the device is not forward biased and it will not start conduction. Remember, in single phase circuits, firing angle is measured from positive zero crossing of source voltage. Therefore, with that statement, what we can write here, for SCR to start conduction, for SCR to start conduction, the condition is alpha should be greater than or equal to theta. Now we can give firing angle at omega t is equal to theta also, okay, nothing wrong. But in that case, SCR will just behave like a diode, because in diode we have already discussed, in diode and RE load, diode started conduction at omega t is equal to theta. In SCR case, if we give alpha is equal to theta, so it will start conduction just like a diode. Next, another important point in this particular case. So generally we will come across this type of statement while doing numerical examples. Suppose given device is SCR and the load is RE. In other words, if load has EMF term and SCR is triggered with constant DC gate current pulse. As per SCR theory, it is not required to supply constant gate current to it. Okay. However, if at all specifically mentioned in the numerical question, it means that if gate current is continuously available, so whenever the device is forward biased, immediately it will start conduction. Whenever you come across that type of condition or statement in the question, it is expected from you to take alpha is equal to theta. In such problems, alpha value will not be given. You can safely take alpha is equal to theta. That is the point. Now, let us draw output voltage. Okay, let us draw output voltage. So just like earlier, what we discussed in the previous case, in this particular RE load, suppose if the device is turned on, load terminal X will be connected to source terminal A, then voltage across XY is the same as AB. Okay. Now, if SCR is not started conduction, then what is the voltage across XY terminals? That is same as E. But in this particular case, as device is triggered at alpha, before alpha, you can draw output voltage is equal to load EMF E. Right? Output voltage is equal to load EMF E. Next, as alpha is given after theta, yet omega t is equal to alpha, what is the sinusoidal value? That is Vm sin alpha. Vm sin alpha is greater than load EMF E. Therefore, we will have output voltage a little bit above this load EMF E, right? Next, that means SCR will start conduction from alpha. Up to what instant it will conduct? Okay, in order to see that, we need to look into current equation. Okay, suppose when SCR is on, when SCR is turned on, what is the basic circuit equation? R into I naught plus E is equal to Vm sin omega t. Therefore, I naught is equal to Vm sin omega t minus E divided by R. SCR started conduction from alpha. SCR will conduct until this current is 0. When this current will be 0? When Vm sin omega t is equal to E. So this Vm sin omega t is equal to E, that will takes place at pi minus theta. Okay. Therefore, SCR conduction will takes place from alpha to pi minus theta. In that interval, output voltage will be same as the source voltage, and output current will have, suppose I can rewrite this equation as Vm by R sin omega t minus E by R minus E by R, right? So it has only sinusoidal term minus some number. What do you mean by that? Output current will simply have the same waveform shape as of output voltage. So with these points, if you draw output voltage and output current waveforms, let us see what type of waveforms we will get. So V0 will start from alpha because SCR conduction started from alpha. So from that instant onwards, load will be connected to source. Now from alpha to the instant where SCR current is 0, that is at pi minus theta. Up to that instant, output voltage will be same as a source voltage, and in that interval, output current will be followed by output voltage. Okay, R and RE loads, output current will simply follows output voltage. At pi minus theta, current reaches to 0. Beyond pi minus theta, SCR will be reverse bias, and hence the device will be in the turn off state. Therefore, we can treat alpha to pi minus theta, this particular interval, as conduction angle. Okay. Next. So in the next cycle, SCR will be triggered at 2 pi plus alpha. Okay, 2 pi plus alpha. So SCR will be turned off from pi minus theta to the instant where the device will start conduction in the next cycle, that is at 2 pi plus alpha. So in this interval, as the device is not in conduction, voltage across XY terminals will be simply same as load EMF E. Okay. So here this is a load EMF E. Now as the device is in the off state, from pi minus theta to 2 pi plus alpha, output current will be 0. Okay. Now, after this, again the same waveform will repeat periodically. The explanation is the same. V0 and I0 waveforms. Okay. V0 and I0 waveform. This is about output voltage and output current waveforms. Now, we need to draw voltage across the device. That is voltage across either SCR or thyristor. Now, if you observe carefully here, let us start drawing Vt waveform from alpha. Alpha to pi minus theta, device is in conduction. Therefore, I can draw safely voltage across thyristor is equal to 0. In this particular circuit diagram, just like earlier, what is voltage across SCR? That is anode voltage minus cathode voltage. As anode is connected to sinusoidal, cathode is connected to load EMF, we can say voltage across SCR is nothing but sinusoidal value minus load EMF. Okay, so let us draw that particular condition here. Now, let us calculate at every instant of omega t what is a sinusoidal value and load EMF. Now, step by step. At omega t is equal to pi, what is the sinusoidal value? That is 0. Therefore, voltage across SCR is 0 minus load EMF E. The net result is a minus E. So, I would like to take that value at this point. Okay, minus E. Next. Yet 3 pi by 2 or 270 degree, what is the sinusoidal value? That is minus Vm. Load EMF E. Therefore, what is voltage across SCR? Minus Vm minus E. Take minus common. So, that is minus of Vm plus E. So, let me take that value here. Next, yet 2 pi, follow carefully here, yet 2 pi, sinusoidal value is 0. So, 0 minus E, that value is minus E. That value is minus E. Next, yet 2 pi plus theta, both sinusoidal value and load EMF E are equal, and hence voltage across SCR will be 0. So, we will get that value here as a 0. Next, yet 2 pi plus alpha, what is the sinusoidal value? That is Vm sin alpha minus load EMF E. As Vm sin alpha is greater than E, you will get that difference as positive. Now, join all of these points. We will get voltage across SCR waveform will be something like this. Okay. Now, 2 pi to 2 pi plus alpha will be same as from 0 to alpha. Okay. 2 pi to 2 pi plus alpha will be same as from 0 to alpha. Okay. Now, what about voltage across this instant at alpha or 2 pi plus alpha? Both are same. Due to space constraint, let me write here. So, this is Vm sin alpha minus E. Vm sin alpha minus E. Next, what is this value? This is minus E. And what about this value? This is minus Vm. Okay, this is a minus Vm. Therefore, we can get peak inverse voltage rating of the device is equal to E plus Vm. This conclusion is same as that of a diode. Next important point is circuit turn off time. How to define a circuit turn off time? The instant where anode current is 0, okay, that is pi minus theta, to the instant where reverse voltage due to external circuit is 0, that is 2 pi plus theta. Okay, so this interval will be treated as circuit turn off time. This interval will be treated as a circuit turn off time. Okay, so this is about the waveforms for RE load. Now from these waveforms, let us write down the conclusions. The first conclusion is conduction angle for the device. What is that? Pi minus alpha minus theta. Okay, basically, okay, let me write down clearly like this: pi minus theta minus alpha. What is the reason for this? SCR is conducting from alpha to pi minus theta, hence we can write it as pi minus theta minus alpha. Okay, next, I naught is maximum at omega t is equal to pi by 2 from the waveforms. Okay, next, voltage across SCR at the instant of triggering. What is that? That is Vt at alpha. Vm sin alpha minus E. Voltage across SCR at the time of triggering is Vm sin alpha minus E. Okay, next, what is peak inverse voltage rating? That is Vm plus E. Peak inverse voltage rating is equal to Vm plus E. Now in our previous discussion, I told one statement: whenever the load is Re nature, which value is preferable to calculate first? That is average output current. So we can write it like this: 1 by periodicity. What is the periodicity? 2 pi is the periodicity. So 1 by 2 pi integration from alpha to pi minus theta. So what is the expression for current here? Vm sin omega t minus E divided by R d omega t, right? Now let us simplify this function. 1 by 2 pi R. Next, what is the integration for sin omega t minus cos omega t minus E into omega t? Next, what are the limits? Alpha to pi minus theta. Okay, alpha to pi minus theta. Therefore, we can further simplify like this: 1 by 2 pi R is multiplied with Vm into, what is the upper limit? Minus cos of pi minus theta. That will give you cos theta, minus of minus plus lower limit, that will give you cos alpha. Okay, minus E into pi minus theta minus alpha. Okay, pi minus theta minus alpha. So it will give you the expression for average output current. Next, once we got average output current, now we can write average output voltage is equal to R into I naught plus E. That is what? Average output voltage expression. Next, now let us write down the expression for output power. What is expression for output power? Power consumed by the battery plus the power that dissipated in the resistor. How can you express power consumed by the battery? E multiplied with I naught plus RMS current square into R, that is power dissipated in the resistor. Next, another important parameter is input power factor. So how to write input power factor expression? Power delivered to the load divided by source volt ampere. So what is P naught? That is E into I naught plus IOR square into R divided by Vs into Is is nothing but IOR. Okay, Is is nothing but IOR. What is the reason for that? If you look into the circuit diagram, here I can say because of simple series circuit, source current is equal to output current. Therefore, RMS value of source current is same as that of RMS value of output current. So, in this expression, what is unknown? That is RMS current. Let us find out that. Now, IORMS, first let us calculate IOR square. 1 by 2 pi integration limits alpha to pi minus theta square of the current function Vm sin omega t minus E divided by R whole square. Integration is with respect to omega t. Okay. Next, let us further simplify this one. 1 by 2 pi r square integration from alpha to pi minus theta. Let us expand a minus b whole square. What we will get? Vm square sin square omega t can be written as 1 minus cos 2 omega t divided by 2 plus E square minus 2Vm E sin omega t. Close the bracket. So, this is the expansion of a minus b whole square. Now, integration is with respect to omega t. Okay. Now, here 1 by 2 pi r square. Now, as we discussed in the diode and RE load circuit, I can follow the same notation. First term Vm square by 2 can be written as Vs square plus E square. So, this term is a constant. Therefore, what is the integration for constant? Omega t. That number multiplied with omega t. Limits from alpha to pi minus theta. Alpha to pi minus theta. Next, minus Vm square by 2 is written as Vs square cos 2 omega t integration 1 by 2 sin 2 omega t. Limits from alpha to pi minus theta minus 2Vm into E. Integration for sin omega t is minus cos omega t minus cos omega t. Now, for this the limits are alpha to pi minus theta. Okay, alpha to pi minus theta. Next, let us substitute the limits. 1 by 2 pi r square Vs square plus E square into pi minus theta minus alpha minus Vs square by 2 into what is the upper limit? Sine of 2 pi minus 2 theta minus sine 2 theta. Lower limit minus sine 2 alpha. If you take minus common, I can make this minus to be plus. Then what should I write? Sine 2 theta plus sine 2 alpha. Okay. Next, here 2Vm into E. Now, what is the upper limit? Cos pi minus theta. So, it will give you minus cos theta. Lower limit minus cos alpha. So, if you take minus common, this plus becomes minus. What should I write? cos theta plus cos alpha. Okay. So for this total term, we should write under root. We should write under root. So this will give you the expression for RMS current. This will give you the expression for RMS current. Now let us take one numerical example. A battery of EMF 150 volt with a series resistance of 8 ohm is charging through a single phase half wave phase controlled rectifier from 230 volt 50 Hz source. The thyristor is triggered with alpha is equal to 35 degree. Determine, first question, average charging current drawn by the battery. Second one, power consumed by the battery. Third one, power dissipated in the resistor. Fourth one, input power factor. Next, PIV rating of device. Next, conduction time. After then, circuit turn off time. Now let us look into the solution. Similar problem we did with the diode and RE load, right? Here also the procedure is the same. So what is the first step? That is theta calculation. What is the expression for theta? Sine inverse E by Vm. So sine inverse 150 divided by Vm is peak value of the source voltage, 230 multiplied with root 2. So this value 27.46 degree or 0.479 radian. 0.479 radian. Okay. Now after this we need to find average value of output current. So first question, let us write down the equation for I naught. 1 by 2 pi r Vm into cos theta plus cos alpha minus E into pi minus theta minus alpha. This is what we have, where alpha is given as 35 degree. Now one cross checking, for this SCR to start conduction, alpha should be greater than theta. 35 is greater than 27.46. Otherwise no need to proceed. Now substitute these values. So that is 1 by 2 pi multiplied with 8. Okay. Next, source voltage peak value Vm is 230 into root 2 into cos 27.46 degree plus cos 35 degree. Okay, minus E is 150 into pi minus theta value in radian 0.479 and alpha value in radian 0.611. 0.611. So if you calculate this value I naught, my calculation was 4.92 ampere. Okay, I naught value I have 4.92 ampere. The next question was power consumed by the battery. Power consumed by the battery. What is the expression for that? E into I naught, 150 multiplied with 4.92. This numerical value is 738 watt. Okay, 738 watt. Next, third question, power that dissipated in the resistor. So before that, we need to find RMS current, IOR square. What is the expression for IOR square? 1 by 2 pi R square into Vs square plus E square multiplied with pi minus theta minus alpha plus Vs square by 2 into sin 2 theta plus sin 2 alpha minus 2 Vm into E multiplied with cos theta plus cos alpha. This is a expression for IOR square. Now in this equation, Vs means 230 volt, Vm means 230 multiplied with root 2. So if you substitute the numerical values, I got IORMS square value is equal to 86.22 ampere. So from this RMS output current, you can take a root for this, 9.285 ampere. Okay, small round off error is fine, no need to worry about it. So anyhow, if at all this type of question comes in the exam, they will consider certain range in order not to penalize the round off errors. Therefore, now power dissipated in the resistor, IOR square multiplied with R, 86.22 into 8. This value, I got this value as 689.76 watt. Okay, 689.76 watt. Next, fourth question, that is input power factor, IPF, is equal to power consumed by the battery plus power that dissipated in the resistor divided by source volt ampere, Vs into Is. Now power consumed by the battery, we got 738 plus 689.76 divided by 230 into what is Is? Is is the same as RMS value of output current, that is 9.285. This value I got 0.6685 lagging. Just like mentioned in the previous question, power factor of rectifier circuit is always lagging. Next, fifth question, that is peak inverse voltage rating, PIV, is equal to E plus Vm. So this value I have 475.27 volt. Okay. Next, sixth question, what is that? Conduction time. Conduction time can be written as gamma T. Okay. So what is the expression? Pi minus theta minus alpha. Pi minus theta minus alpha. So pi minus, what is theta in radian? 0.479 minus alpha 0.611 is equal to, okay, I have not calculated this value. So gamma T in time will be, you have to divide this with omega, okay, or omega value is 100 pi. I have this value readily, that is 6.53 millisecond. That is what? Conduction time in millisecond. Next, circuit turn off time, that is pi plus 2 theta divided by omega. Basically omega Tc is equal to pi plus 2 theta. So pi plus 2 into 0.479 divided by 100 pi. This value will come around 13.05 millisecond. So these are different calculations for this problem. Now after this problem, I would like to give you one exercise. Follow carefully. If you observe this problem and a diode RE load in the previous lecture, if you notice carefully, same data I considered. There also 8 ohm 150 volt and the source voltage is 230 volt. Because of SCR is taken as a device, I gave alpha is equal to 35. So what I want you to do, compare these numerical values of I naught, power consumed by the battery, power dissipated in the resistor and input power factor, okay, with the diode circuit and SCR circuit. And then what you can do, prepare a small table and write down the conclusions on your own, okay, in your short notes. So when SCR is used, in other words, when alpha is increases, what is happening to these values, right? So from the numerical question, they will ask you values directly. Otherwise, from the analysis wise, when alpha increases, which of the following parameters will increase or decrease? Different options will be given. One or more than one options may be true. Okay, so multiple select questions also we can frame from these numerical problems. So in case of a conventional exam, you can take this problem as a 20 marks question. In the objective exam, when alpha is increases, what will happen to these values? When alpha decreases, what will happen? Otherwise, if SCR is replaced with a diode or diode is replaced with SCR, whether these values increase or decrease, there is no change. That type of questions we can frame from objective exam. Okay, so practice these problems one more time after watching this video. Next, let us take another load. In the previous load, we considered RE. Now, I just added an inductance. Therefore, this load is a RLE load. The physical example for this load is a DC motor. You can say separately excited DC motor. First, before starting the analysis, here also few basic parameters. Theta is sine inverse E by Vm. For SCR to start conduction, alpha should be greater than or equal to theta. So if you see these waveforms here, alpha is given in such a way that it is after theta. In fact, the previous waveforms lines only I would like to continue. So in this particular case, what are the waveforms are interested for us? Output voltage, output current and voltage across the device. Now here, before going to the waveforms, first I would like to look into output current equation from the differential equation. Suppose if SCR is turned on by satisfying alpha is greater than or equal to theta, what is the basic circuit equation? R into I naught plus L into d I naught by dt plus E is equal to source voltage. Okay. So first let us write down that basic equation. When SCR is on, the circuit equation is R into I naught plus L into d I naught by dt is equal to Vm sin omega t. Okay. Now we can rewrite this equation as r I naught, I'm sorry, d I naught by dt plus r by L into I naught is equal to Vm by L sin omega t minus E by L. Okay, minus E by L. Now observe carefully here, right hand side there are two terms. Right hand side there are two terms. So let us solve this equation from the basics. So what we need to calculate first? Integrating factor. Integrating factor is equal to e power integral r by L into dt. This will give you e power r into small t divided by L. Okay. After that, how can we write the solution? How can we write down the solution? I naught multiplied with integrating factor e power rt by L is equal to integral q. Now q has two terms. Therefore, let us write down the integration separately. What is that? Vm by L e power rt by L multiplied with sin omega t dt minus integral e by L e power rt by L dt plus k, right? Now let us further simplify this integration. I naught multiplied with e power rt by L is equal to, now in our previous diode circuits we simplified this integration. What is that? Vm into e power rt by L denominator square root of r square plus omega L whole square. Okay, square root of r square plus omega L whole square multiplied with sin of omega t minus phi. Next, minus e by L, okay, into, what is the integration for this term? E power rt by L. Now the denominator is r by L plus k. Now we can cancel this L and L, right? Now we are interested in the expression for current I naught. Therefore, we don't want this term to be multiplied at the left hand side. So what can I do? Divide both sides with that particular term. Therefore, we will get I naught is equal to Vm divided by square root of r square plus omega L whole square multiplied with sin of omega t minus phi minus e by r. Okay, exponential term will be cancelled because we are dividing both sides with that number, plus k into e power minus rt by L. Let us write, this is equation number 1. Now what is required for us? We want the expression for I naught where k is unknown in this equation 1. So we have to eliminate that k value. So how? In other words, we need to find that k value by using initial condition. What is initial condition? That is, I naught is equal to 0 at omega t is equal to alpha. I naught is equal to 0 at omega t is equal to alpha. Now let us substitute that one. left hand side 0, right hand side Vm divided by square root of r square plus omega L whole square multiplied with sine of alpha minus phi minus E by R plus K into E power minus R by L into alpha by omega, because omega t is equal to alpha means t is equal to alpha by omega. So from this we can write K value is equal to E by R minus Vm divided by under root R square plus omega L whole square multiplied with sine of alpha minus phi into E power R alpha divided by omega L. Okay, let me say this is a 2. So this equation 2 will give you that K value. So what can I do now? Substitute K value from equation 2 into equation 1. Then what we will get? Let us see. I naught is equal to, let me write down here, I naught is equal to Vm divided by root of R square plus omega L whole square into sine of omega t minus phi minus E by R. Okay, minus E by R. Now we need to multiply K value with E power minus RT by L. So for that, what I can do? K value, first term in K value, that is plus E by R into E power R alpha by omega L. This first term in K value should be multiplied with E power minus RT by L. Okay. Next, second term in K value, let me write down here, minus Vm divided by root of R square plus omega L whole square into sine of alpha minus phi into E power R alpha by omega L multiplied with E power minus RT by L. Okay. Now I can rearrange this term like this. I naught is equal to, now observe carefully, from the first term and last term I would like to take this particular Vm by under root term common. Then what we will get? Vm divided by root of R square plus omega L whole square multiplied with sine of omega t minus phi, I am taking that term as a common, minus sine of alpha minus phi into E power minus R by omega L into omega t minus alpha. Okay, we can combine these two terms like this, just like in the previous discussion. Next, second and third terms, can we combine it like this? So here continuation, minus E by R into E power minus E by R, I am sorry, into 1 minus, okay, into 1 minus E power minus R by omega L into omega t minus alpha. Okay, so here one more bracket. In this equation where phi is equal to tan inverse omega L divided by R. Okay. So this is the expression for current flowing through the circuit, right? Of course, equation looks a little bit lengthy, but observe carefully, there is no new term in this total equation. All of the terms are known to us. What are that? Vm by root of R square plus omega L whole square, anyhow it is a constant, no need to worry about that. Sin of omega t minus phi, this particular term will tell you that current flowing through the circuit has sinusoidal expression. Minus sin alpha minus phi is a number. So this one exponentially decaying component. Minus E by R is also a number. Second term is exponentially decaying component. Even though equation looks a little bit lengthy, but the two major terms which will decide the waveform shape, those are sinusoidal term and exponentially decaying component. Therefore, what is the point to understand at this stage? Whether the load is either RL load or RLE load, the waveform shape will be purely decided by two terms. One is sinusoidal and another is exponentially decaying component. Okay. So, whatever I0 waveform we had earlier for RL load, the same I0 waveform is applicable for RLE load also. So, what I can do here, from alpha to beta, follow carefully, from alpha to beta, output current waveform will be just similar to sinusoidal and exponential decaying component what we discussed in the RL load. So this is alpha and this is a beta instant, right? Now before alpha, as the device is not yet started the conduction, the output voltage is equal to load EMF E. Okay. Next, from alpha to beta, as the load current is flowing through the circuit, output voltage will be same as that of the source voltage because thyristor is in conduction. Therefore, from alpha to beta, output voltage will be same as that of source voltage. But we know that at alpha, output voltage will be greater than that of this E, because Vm sin alpha is more than load EMF E. Now from alpha to beta, if you draw the output voltage which is just similar to that of source voltage, then V0 waveform it looks like this. V0 waveform it looks like this. Yet omega t is equal to beta, current is 0, hence the device will get turn off. So from beta to the instant the device triggers again in the next cycle, output voltage will be same as that of load EMF E. Output voltage will be same as that of load EMF E. Okay. Next, yet 2 pi plus alpha, when the device is triggered again, then output current will have sinusoidal and exponentially decaying component, so that the output voltage will be something like this. Okay, and once the device is turned off here, output voltage will be followed by load EMF. So this is how V0 and I0 waveforms. Now from this waveform, the first observation is SCR is in conduction from alpha to beta. SCR is in conduction from alpha to beta. Okay. Next waveform, voltage across the device. Next waveform is voltage across the device. So we know that as device is in conduction from alpha to beta, you can safely draw voltage across SCR will be 0. Now in this case also, voltage across SCR means anode voltage, that is the sinusoidal value, minus load EMF E. So now you may have a question, when I am defining sinusoidal value minus load EMF, you may have a question that what about this resistor and inductor? Now observe carefully. After beta, once the device current becomes 0, the voltage drop across the resistor will be 0. The voltage drop across this inductor is also 0. Then voltage across SCR will be same as sinusoidal value minus load EMF E. So let us draw that. Now follow carefully. At omega t is equal to beta, what is the source voltage here, anode voltage? That is Vm sin beta minus load EMF will give you voltage across SCR. Anyhow, that value will be negative, so it will be a little bit below x-axis. So I can say that this is Vm sin beta minus E. Next, at 270 degree, what is sinusoidal source value? That is minus Vm, okay, minus Vm. So minus Vm minus E will be equal to voltage across SCR. That value I can take it somewhere here, minus of Vm plus E. Next, at 2 pi, sinusoidal value is a 0 and load EMF is E. Then 0 minus E, it will give you minus E. Let us take somewhere here. Now I am extending 2 pi plus theta line. Okay, so at 2 pi plus theta, at 2 pi plus theta, both sinusoidal and load EMF both are equal. Hence the difference will be 0. It will touch here, x-axis. At 2 pi plus alpha, what is the sinusoidal value? That is Vm sin alpha minus load EMF E will give you Vt. Therefore, that value will be somewhere here. Now join all of these points. By joining all of these points, we will get voltage across SCR waveform will be something like this. Now here 2 pi to 2 pi plus alpha waveform will be same as from 0 to alpha also. 2 pi to 2 pi plus alpha waveform is the same as from 0 to alpha also. Okay, so this is about voltage across SCR. Now let us write down few conclusions here. What are that? Voltage at this instant, voltage at this instant is Vm sin alpha minus E. Voltage at this instant is Vm sin alpha minus E. Next, at 270 degree, what is this voltage? Minus of Vm plus E. Minus of Vm plus E. Next, at 2 pi, this voltage value is minus E. Okay, this voltage value is a minus E. Now these are the waveforms for single phase half wave phase control rectifier with RLE load. One more parameter here. What is the circuit turn off time? Circuit turn off time is measured from the instant at omega t is equal to beta to, that means where anode current is 0, that is at beta, to the instant where reverse voltage due to this external circuit is 0, that is at 2 pi plus theta. Okay, so this interval will be treated as circuit turn off time. So this is about the waveforms. Now let us write down the conclusions. Now the first conclusion is conduction angle for SCR, gamma T. SCR is in conduction from alpha to beta, hence we can write gamma T is equal to beta minus alpha. Next, circuit turn off time omega Tc is equal to 2 pi plus theta minus beta. Okay, 2 pi plus theta minus beta, or Tc is equal to 2 pi plus theta minus beta divided by omega in second. Okay, so that is what circuit turn off time. Next, peak inverse voltage, please refer the waveforms. Vm plus E, peak inverse voltage is equal to Vm plus E. Next, voltage across SCR at the instant of triggering. What is that? See the waveform. Vm sin alpha minus E. Similarly, voltage across SCR at the instant of turn off, that value is Vm sin beta minus E. You have a look at the waveform. Okay, next one. So one more point here, in case of RLE load, it is preferable to calculate average output voltage first, whereas in our earlier circuit RE load we told that average output current is preferable to calculate. Don't confuse, sometimes R is calculating I0, sometimes calculating V0. It is all just for convenience. Okay, why? Because if you look into the waveform here, if you try to find average output current expression, you have to integrate I0 equation from alpha to beta. You have to integrate I0 equation from alpha to beta. Expression for this I0 is very lengthy equation. Integration of that particular expression is a gone case. Okay, so it is preferable to find average output voltage. If you look into one cycle, I can say alpha to 2 pi plus alpha will be one cycle. So how can you write down the limits? Alpha to beta is one limit, beta to 2 pi plus alpha is another limit. Okay, now let us write down average output voltage capital V0 is equal to 1 by 2 pi. 2 pi is the periodicity. 1 by periodicity. So 1 by 2 pi. Now integration limits alpha to beta Vm sin omega t d omega t plus integration from beta to 2 pi plus alpha. So that alpha we started, 2 pi plus alpha will stop. So one cycle is completed. What is the expression? That is E d omega t. E d omega t. Now let us simplify here. 1 by 2 pi Vm multiplied with minus cos omega t limits from alpha to beta plus E into omega t limits from beta to 2 pi plus alpha. Okay. Now what is the simplification here? 1 by 2 pi Vm upper limit minus lower limit will give you cos alpha minus cos beta plus E into 2 pi plus alpha is the upper limit minus beta will give you the lower limit. So this is equal to the expression for average output voltage. This is the expression for V naught. Okay. This is the expression for V naught. Next. Now, for example, if you look into output voltage equation, V naught is equal to R multiplied with I naught plus L into d I naught by dt plus E, right? So, if you convert this equation into average terms, if you convert this equation into average terms, capital V naught is equal to R multiplied with I naught, where capital I naught is average current, plus LdI by dt average value is 0 plus E. Okay. Now, from this equation, we can write I naught is equal to V naught minus E divided by R. V naught minus E divided by R. Now, observe carefully. When you are calculating average output current, inductance will not play any role in the average value. So, this is what we will have a general equation in case of DC motor also. Suppose in our circuit between X and Y terminals, if you consider load as a separately excited DC motor, armature current, which is output current of the rectifier, is equal to terminal voltage, right, minus EB back EMF divided by armature resistance. This formula is also in line with the DC machine. Okay, this is about RLE load analysis. Now, let us take one numerical example. A single phase 1 pulse converter with RLE load has the following parameters: supply voltage 230 volt 50 Hz, load resistance of 2 ohm, inductance is 1 millihenry, and the load EMF is 120 volt. Extinction angle is 220 degree, that is beta, and firing angle is 25 degree. First question, calculate the voltage across SCR at the instant of triggering. Second one is, find the voltage that appears across SCR when current decays to 0. Next, PIV, average output voltage and current, circuit turn off time. Now, let us look into the solution. Okay. So, what is the first question? Voltage across SCR at the instant of triggering. Okay. So, what is the expression for this? Vm sin alpha minus E. What is Vm here? That is 230 into root 2 multiplied with sin alpha, that is sin 25 degree, minus load EMF is 120. So this value I calculated and I got 17.46 volt. 17.46 volt. Okay, next. Second question. The voltage that appears across SCR at the instant of current is 0. What do you mean by that? Vt at beta. What is the expression for this? Vm sin beta minus E. Okay. So let us substitute the numericals. 230 into root 2 multiplied with sin 220 degree minus load EMF, that is 120. So this will give you, I got this value as minus 329 volt. Okay, minus 329 volt. Next question. Question C. That is PIV rating of the device. PIV is equal to load EMF E plus Vm. Okay, so what is that? 120 plus 230 multiplied with root 2. This numerical value is 445.27 volt. Okay, next, fourth question, that is average output voltage V naught. What is the expression? 1 by 2 pi Vm multiplied with cos alpha minus cos beta plus E into 2 pi plus alpha minus beta. Okay, close the bracket. Now, by substituting these values, okay, if you want, let me write down. 1 by 2 pi Vm is 230 into root 2 multiplied with cos alpha, that is cos 25 degree minus cos 220 degree plus E value is given 120 into 2 pi plus, now you have to substitute alpha value in radian. That value is 0.4363 minus 3.84. So this calculation is 141.57 volt. That is the average output voltage equation. After that, average output current V naught minus E divided by R, where V naught is 141.57 minus E 120 divided by load resistance is 2 ohm. This value is 10.785 ampere. Okay. Now, the last part of the question, that is circuit turn off time. Tc is equal to 2 pi plus theta minus beta divided by omega. So in this calculation, what is theta value? Where theta is equal to sine inverse 120 divided by 230 into root 2. This value is equal to 0.378 radian. Therefore, if you substitute those values, 2 pi plus theta value we got 0.378 minus beta value in radian 3.84 divided by omega is 100 pi. So this value is equal to 8.98 millisecond. So these are all the various answers. Now let us look into whatever we discussed till now, that is a half-wave rectifier circuits. Just one recap. Listen carefully. This is a very important discussion. At the end of this discussion, we will get one interesting conclusion. Now take any one half-wave rectifier circuit. A simple example is a diode and a resistive load. Here I have drawn quickly the current waveform at load side, I0 waveform. What is I0 waveform here? That is from 0 to pi, this peak value is Vm by R, because basically I0 is nothing but V0 by R, right? Next, pi to 2 pi, as the diode is in turn off, current is 0. This is what we studied in our diode half wave rectifier circuit. Now one important question here, can you tell me what is I0 waveform? I can say this waveform is a DC waveform. Okay, what is the reason for that? Area under that waveform is finite value. It has a DC component, right? Of course, it is not a pure DC, whatever, it is a basically DC waveform. Next, if you look into source current waveform, now just think about what is the source current nature. Generally, rectifiers means the basic definition is AC power to DC power conversion. True. So we can expect that at this stage, source current will have AC nature, but that is not true in case of half wave rectifier circuit. What is the reason for that? Because of this simple series circuit, we can write IS is equal to I0, right? IS is equal to I0, where this I0 is equal to V0 by R, where this I0 is equal to V0 by R. Basically, this waveform is a DC waveform. Therefore, what do you mean by that? Source current is not pure AC waveform. Okay, it has something else. We'll see what is a full picture of this waveform. Otherwise, I can write down directly. So we know Fourier series expression for this V0 waveform. In the beginning, we calculated for in the Fourier series lecture. So what is Fourier series analysis for V0 waveform? That is Vm by pi plus Vm by 2 sin omega t minus 2Vm by 3 pi cos 2 omega t minus 2Vm by 15 pi cos 4 omega t and so on. This is the Fourier series expression for V0 waveform. Now, if we divide with a resistance, then we will get current expression. Now, what is the important point here is, this particular term is DC component and this term is fundamental component. Okay, and these terms are even harmonics. These terms are even harmonics. So what is the significance or a consequence of these various components? Now, if you observe closely here, input for any rectifier circuit basically will be taken from some transformer circuit. Okay, input for any rectifier circuit basically will be taken from some transformer circuit. Therefore, what is the concept of half wave rectifier circuit? Half wave rectifier circuit concept is as equivalent of a diode is placed in the secondary of some transformer. Therefore, I can say that secondary current of this transformer I2 is equal to source current of the rectifier. Okay, source current of the rectifier. So what we can say here, as per this Fourier series analysis, now source current or secondary current of the transformer is not a pure sinusoidal. That is because of half wave rectifier action. Okay, so what are various components that source current or secondary current of transformer contains? One is DC component, another is fundamental component, and the final components are even harmonics. But you might studied in the transformers course What is the transformer basic concept? Transformer will operate on constant flux or MMF balance concept, right? That means suppose whenever load is connected, some I2 will be flowing in the secondary side. Whenever load is connected, some I2 will be flowing in the secondary side. So as per transformer concept, primary will supply balancing for every sinusoidal component of I2. So that you can draw here in this way, okay. So you can call it as either I2 dash or I1 dash, right? I don't know what symbol you have used in transformers course. So either I2 dash or I1 dash. So the point is primary will supply balancing for every sinusoidal component of secondary current. Every sinusoidal component of secondary current. That is an important point to understand here. But due to diode at the secondary side, secondary current has DC component. Secondary current has a DC component. So primary will supply balancing for sinusoidal components. So we need not worry about these components. Okay. Of course, harmonics, because of the harmonics, harmonic power drawn by the machine will increases, core loss will increase. That is one drawback. That is okay. But here main culprit in this total discussion is DC component. Okay. Secondary current of the transformer or source current of the rectifier contains DC component. Okay. Because of this DC component, now the secondary side or magnetic circuit of the transformer will move towards saturation. So the DC component of this source current or secondary current of transformer will result into saturation of source transformer. Okay, saturation of source transformer. So this is the basic drawback of half-wave rectifier circuit. Try to understand very carefully. Input for any rectifier circuit will be taken from some transformer side. Half-wave rectifier action is as equivalent of placing a diode in the secondary of a transformer. Okay. Therefore, what will happen here? Source current or I2 of a transformer will have DC component. The behavior of this DC component will make magnetic circuit of the transformer towards saturation. Therefore, half-wave rectifier circuits are not preferable for half-wave rectifier circuits are not preferable for high power applications. When you use it in high power applications, then what will happen? The DC component magnitude will be very high. Because of that, source transformer saturation will take place very quickly. So half-wave rectifier circuits are not preferable for high power applications. But in order to use in high power applications, what is the solution? So if you understand what is the reason for this problem, then you can think about the solution. What is the reason or what is the main culprit in this explanation? That is DC component. Because of this DC component, source transformer is moved towards saturation. Therefore, in order to avoid that, what you need to do? To use the rectifier circuit in high power applications, we should eliminate this DC component. We should eliminate that DC component. Elimination of DC component is nothing but you make this area under the waveform to be 0, then DC component will be 0. When you will have area under the waveform will be 0, that is possible only when negative half cycle is also present. But as long as you have single diode in the circuit, we will not have negative half cycle, isn't it? As long as there is a single diode or single thyristor in the circuit, you cannot create negative half cycle, right? Therefore, in order to use it in high power applications, DC component should be eliminated. For that, negative half cycle in the source current should be created. Okay, negative half cycle in the source current, not in output current. Negative half cycle in source current should be created. That is not possible with a single diode. Then use multiple diodes. So, in order to eliminate DC component using multiple devices, okay, using multiple devices, we will study that circuit in a circuit named full wave rectifier, in a circuit called full wave rectifier. Okay, so this is the introduction to start full wave rectifier. With this we completed half wave rectifier analysis. So what is the main drawback of half wave rectifier circuit? Source current contains DC component. Okay, key points. Because of that, source transformer will move towards saturation. Hence, it is not preferable for high power applications. To use it in high power applications, DC component should be eliminated. Okay, that can be possible with the help of a full wave rectifier circuits. So, how to eliminate that DC component and what are different waveform shapes of source current and whether it is a pure sinusoidal or any harmonics are there, we will study all of those details in full wave rectifier circuit. Before going to full wave rectifier circuit, there is one more basic concept. Let us look that into. Now, look into these two circuits. Now, here the question is, in the first circuit, which diode or diodes will be in conduction? You might studied about these type of circuits in analog electronics. Now, just let us look into quickly. So, in the first circuit, the diode is connected to higher positive potential, that is a 10 volt. This particular diode will be forward biased, isn't it? Therefore, this plus 10 volt will appear at this point, and hence what is anode to cathode voltage for D1? That is 5 volt minus this 10 volt. So what is the difference of that? 5 minus 10, that is a minus 5. Therefore, D1 will be reverse biased. Okay. Next, D5 voltage minus 5 minus 10 minus 15 volt. Therefore, in this particular circuit, D3 only forward bias. D3 only forward bias. Now, in the second circuit, with a similar explanation, D6 only forward bias. Okay. So, when D6 is forward bias, this minus 10 volt will appear at this point, so that minus 10 minus of minus 5. So, the difference will be D4 anode to cathode voltage is minus 5 volt. D2 anode to cathode voltage minus 10 minus 5 minus 15 volt. Therefore, in this particular circuit, D6 only forward bias. D6 only forward bias. So, here conclusion is, now observe carefully, the first circuit, cathodes for these three diodes are connected at a common point. So, this first circuit is called common cathode configuration. Common cathode configuration. Now, the second circuit, anodes of all these three diodes are connected together at a common point. Therefore, second circuit is called common anode configuration. Okay, common anode configuration. So, going forward for the full wave rectifier analysis, these two configurations are very important and these are the basic circuits. In common cathode configuration, the diode which is connected to higher positive potential will be forward bias. Remaining devices will be in reverse bias. Similarly, in common anode configuration, the diode which is connected to higher negative potential will forward bias. Remaining devices will be reverse biased. Okay. So, this is about basic concepts in order to start our full wave rectifier analysis. We will see full wave rectifier analysis in the next lecture. With this, I will conclude this lecture. Thank you.